Hello everyone, Mehdi Mortazavi here, and today we are going to use one of the correlations we learned earlier regarding the properties of real gas. So, we have a problem to solve, and in this problem the question is asking for the enthalpy of the nitrogen gas at a certain temperature, 175 Kelvin, and at a certain pressure, which is 8 megapascal. And in part A, the question is just asking to use the data from the ideal gas table. So basically we have some listed properties, and in those tables it is assumed that the gas is behaving ideally. But before I jump and use those tables, let's see whether nitrogen is behaving as an ideal gas at this temperature and at this pressure. So basically we know that gases behave either based on the ideal gas law. So let's say gases behavior can be described either by the ideal gas law or based on real gas. So in another language, a gas is behaving either ideally or as a real gas. And let's see what is the difference between them. In ideal gas law, or let's say in both of them, the equation of state is PV equal to ZRT, and here PV, V being the specific volume, equal to ZRT. So in both of these two cases, the gas is behaving or following these two correlations. So basically they are pretty much the same, but the only difference between them is the Z value. Whenever we are discussing about an ideal gas, then that Z is equal to 1. So because of that, usually we go with PV equal to RT. We don't even write this down. But when it comes to real gas, this Z value is not equal to 1. Okay? So if a gas is following equation PV equal to RT, then that gas is behaving ideally. Now, there is a way to figure out if that Z is equal to 1 or any other number. And what I would like to do, although the question is not really asking for that, is not really asking for the Z value, but I would like to obtain the Z value, and based on that we can judge whether the gas is behaving ideally or not. So we learned about how to find Z back in thermodynamics 1, but let's do it once again. In order to find Z, there are two properties that I need to find. I need to find the reduced temperature, T subscript R, which is temperature divided by the critical temperature, right? And let's say the temperature is given at 175 Kelvin, and the T critical temperature is coming from table A1. So if you go to table A1, you should be able to obtain the critical temperature for nitrogen equal to 126.2 Kelvin. Okay, and this will give you a reduced temperature of 1.38. So this TR is a reduced temperature. Also, we need to find the reduced pressure, which is PR, and that PR is pressure divided by the critical pressure. So once again, the critical properties are coming from table A1. You will need to obtain that. Table A1. Same thing with this one here. Okay, so the pressure is given at 8 megapascal, and if you go to table A1, you will be able to obtain the critical pressure, which is 3.39 megapascal. So just be careful that the unit of the critical pressure in that table is megapascal. So if your pressure unit in the problem statement is something other than the megapascal pressure, you need to do the unit conversion. Just be careful with that. So this gives us the PR value equal to 2.35. And both of these two numbers, this one and this one, they are dimensionless numbers. They are unitless numbers because this is temperature divided by temperature, and this is pressure divided by pressure. So there should not be any unit in front of them. Now, the next step to find the Z value, like this value, this property, or this property we had here, is to go to table or figure, I should say, A15 from your textbook. So if you go to figure A15, let me correct this because this is not really a table. Let me correct. So if you go to figure A15 in your textbook, you will see something like this. We went through that back in term 1 a lot. And I'm going to have another video just to discuss how to obtain this. But for now, let's do it really quick. So this A15 shows two figures. What we want to use is the figure in the bottom because of the range of PR. So the horizontal axis is PR. If that is too small, definitely take a look at your own table. So this is A15 from the textbook that we are using. PR is the horizontal axis, and TR is something which is given here on these curves. So we are looking at some green curves, and here it says TR equal to 5, TR equal to 2.5, and etc. So what you want to find on the horizontal axis, which is PR, you want to find the range of your PR. So in this problem, our PR is equal to 2.35, right? So let's say this is 2 and this is 2.5. So 2.35 is obviously between these two. I would say maybe something somewhere here. So imagine a vertical line at that PR value. So the next step is to find the corresponding green line, which is the TR, and find the junction between them. So our TR was 1.38. So this is TR 2.5, 2, 1.8, 1.6, 1.5, 1.4, and 1.3. So our green curve is between this curve and this curve. It doesn't really directly show curve for 1.38. So definitely we want to use some engineering sense. So 1.38 is closer to 1.4. So this is basically the curve that you want to follow. All right. And our PR, where was it? Like was somewhere here, 2.35. So let's say, I'm sorry, this is 2 and this is 2.5. So our 2.35 is something here. So that is my 2.35. And my green curve is 1.4 here, but we are slightly less than that. So let's say this is our point, just roughly. Obviously, you want to go crazy with that. So this is your point, and for the next step, you want to go horizontally to the left and read your z value. So I would say our z is probably 0.7, definitely greater than 0.75, because here is 0.75, but this is our point. Let's say 0.76, for example. Just roughly 0.76, 0.78, 0.77. So our z is just roughly RZ is roughly 0.77, and this Z itself is a dimensionless number. Now, if I get back into here, we will see that RZ is not equal to 1, obviously. It's different from 1. So definitely nitrogen is not behaving as an ideal gas. So nitrogen is behaving as a real gas in this condition, in this temperature and this pressure. So first of all, the conclusion is nitrogen is behaving as a real gas at the given condition. Okay, in another word, nitrogen is not behaving as an ideal gas. Okay, so in part A, well, again, we didn't really need to, the question didn't really ask for this calculation, but that was just for practice and see whether the gas is behaving ideally or not. In part A, the question is asking to use the ideal gas tables. Okay, so definitely the title reads ideal gas. It means the answer we are going to get in part A is not definitely correct, because this table is prepared by assuming that the gas is behaving ideally, but nitrogen in this condition is not behaving ideally. So if you go to the corresponding table, you will see that H is equal to so before giving you the number, the question is what table do we need to use? So let me walk you through the tables. The table that we need to use is basically table A18. So the title reads ideal gas properties of nitrogen. So this is exactly the table that we want to use, because before that 17 is for air and 19 is for oxygen. So A18 is the one that we want to use. Now in this table, if you see, properties are listed for temperature. Okay, so we have H bar, U bar, and entropy. Now, the temperature that we have in the problem statement was 175 Kelvin, right? The very first line that we have is 0 Kelvin, or absolute zero they call it. And then the next one is 220 Kelvin. So obviously we need to do some interpolation between those two to find the H value. But even if we do that, look at the unit. The unit says kilojoule per kilomole. Look at the problem statement. The problem statement is asking for kilojoule per kilogram. So you want to be careful with the unit conversion. So what I'm going to do, I'm going to do the interpolation to obtain the enthalpy H bar at our temperature, which is 174. The unit of that enthalpy is going to be kilojoule per kilomole. So for the next step, I need to work with the unit to convert it to kilojoule per kilogram. So by doing some interpolation, we will obtain H bar equal to 5083.7 kilojoule per kilomole. All right, so this is coming from table A18 from your textbook. Okay, but the unit needs to be converted. In order to convert the unit, what I'm going to do, I'm going to multiply this H bar multiplied by the inverse of the molar mass, because the unit of molar mass is kilogram per kilomole, but if I make the inverse, then I will have the correct unit. Let me show you how. So I would say H that I'm looking for in kilojoule per kilogram is H bar multiplied by the inverse of molar mass. And here, this H, the first one, let's say this is in kilojoule per kilogram that I'm looking for. Let's say this H bar is in kilojoule per kilomole that I already have, and M itself is in kilogram per kilomole. So we learned about this capital M earlier, and this capital M is basically molar mass. And you can obtain that in table A1. So that gives me H value is equal to, instead of H bar, I have 5083.7 kilojoule per kilomole multiplied by the inverse of M, or the inverse of molar mass, which is 1 over 28.013, and the unit is going to be kilogram in the denominator and kilomole in the numerator. All right, now what happens, this kilomole will be cancelled with this one, and I will have H equal to 181.4 kilojoule per kilogram. So each 1 kilogram of nitrogen has 181.4 kilojoule of enthalpy, but once again, this is by assuming that nitrogen is behaving ideally, but in fact we know that nitrogen does not behave as an ideal gas. So this is answer to part A, okay, from ideal gas tables. Okay, now let's go to part B. In part B, the question is asking to use the generalized enthalpy departure chart. Okay, now what we need to do, in fact, for part B is to go back to our previous discussion we had. So if you remember, this was one of the equations that we discussed in previous videos. The equation looks pretty scary, but in fact, it's not that complicated to use this correlation. So what we have here is two series of H, or actually H bar in this particular case. We have two series of H. One of them is for a real gas, and the other one on the right hand side has the subscript of ideal gas. So on the left hand side, we have the change in enthalpy of a real gas in right hand side we have change of enthalpy of an ideal gas. And then we have the universal gas constant, the critical temperature, and ZH, which is called enthalpy departure factor. Now, here is what. This correlation is obtaining the difference in enthalpies whenever the gas is going from state 1 to state 2. All right. In this particular question, there is no two states. All we have is just one state, like the combination of temperature and pressure gives me one state. There is no two state. There is just one state, okay? So that means I can rewrite this correlation and easily get rid of all terms with subscript 1, let's say, because all I need to work is just one state. I can get rid of all subscript 1s and just work with 2. Or likewise, I can get rid of all subscript 2s and just work with subscript 1. Both of them give me the same answer. So first of all, let me start by writing down the equation and do some simplification. So I'm doing part B. In part B, I am using that scary looking equation that we had earlier. So once again, this correlation is for the condition of having two different states. This correlation gives the change in enthalpy when the gas changes state from state 1 to state 2. So this correlation gives the change in enthalpy when the gas changes state from state 1 to state 2. However, in this particular problem, we are just dealing with one state. In this problem, we are dealing with only one state. Okay, so there is no change in state, right? So that means I can still use that correlation, but I may need to cancel one of the subscripts. So what I would do, I would go back into the same equation and I would get rid of all subscript 1s, simply because I'm only dealing with one state. So basically I will end up with H bar real gas is equal to H bar ideal gas minus RU T critical ZH. So this ZH is coming from the chart, all right? So the title is going to be enthalpy departure factor, which is coming from figure A29. So right now, the left-hand side is our question mark. Like this is what we need to find on the left-hand side. Okay, so let's do that. What I'm going to do, I am going to basically obtain the left-hand side by knowing this value. We already had that. We already got that in the previous step. And then I'm going to do the math. So basically, H bar real gas is equal to, instead of this H bar ideal gas, I am going to use this value because this is the one that we got from the ideal gas table, right? And that is also in H bar, and I just use the same number. So 5083.7 kilojoule per kilomole minus RU is the universal gas constant, which is equal to 8.314 kilojoule per kilomole Kelvin. You do not need to memorize this value. Obviously, you will need that for the problems, but you can obtain it in table A1. At the very bottom of the table, it lists these numbers. Let me show you, because you will need that in the problems. Also, you need the unit. So go to A1. This is A1, right? This is the table. Right at the very end of the table, here it says RU is equal to 8.314 kilojoule per kilomole Kelvin. This is where you can obtain RU value. So that RU is called the universal gas constant. And as the name says, it's a constant number no matter what gas you are using. We have the same number for air, for hydrogen, for argon, for nitrogen, you name it. All of them are using the same RU value. So the next property is T critical. Again, at the very beginning, I obtained T critical from table A1, and that was 126.2 multiplied by 126.2 Kelvin multiplied by ZH. So I need to have that ZH value. So this ZH comes from figure A29. The name of this ZH once again is enthalpy departure factor. So if I want to find ZH, I need to have my PR and TR. And the good thing is at the very beginning, I already obtained the reduced temperature and the reduced pressure. Okay, so you go to the same table, you go to figure A29, and based on that, you should be able to find your ZH value. So let's say for TR equal to 1.38, for PR equal to 2.35, you go to the table and read ZH value. So let's do that together. All right, so this is what you want to use. Let me show you the title. It says A29. What I have here on the horizontal axis, I have PR, reduced pressure, and these green curves, they are my reduced temperature. So as before, you want to start by finding your PR first. Our PR is 2.35. This is PR equal to 1, 2, 3. So obviously we are between these two, but the thing is, the scale of these axes is not linear, it is logarithmic. So you want to be careful. That means my point 2.5, for instance, is not really between 2 and 3. Let's say 2.5 is closer to 3 because this is on logarithmic scale. But that shouldn't really make any problem for us. We don't really want to go crazy. We just go roughly to obtain the ZH value. By the way, the vertical axis is ZH, in case I forgot to mention. So once again, the horizontal axis is PR, or the reduced pressure. These green curves are TR, or the reduced temperature. So you see different numbers, 0.5, 0.55, 0.6, 0.65, all the way to the largest TR that we see, I think, is 4.00. Okay, so PR, TR, and the y-axis is ZH that we are looking for. So the procedure is obtain your PR, which is 2.3. So let's say somewhere here, right? And our TR, the reduced temperature, is 1.38. So let's say this is 1.4, this is 1.3. So let's say we are closer to this one. I'm continuing 2.35 again. So let's say the pencil line is 2.35. This is 1.4, but we are slightly above 1.4. Let's say we are here. So my ZH is less than 1.5. Let's say the ZH value, let's say we are here. So let's say the ZH value is 1.4, just roughly. So for ZH, is roughly equal to 1.4. And once again, this is a dimensionless number. So if I put it here 1.4 without any units, that gives me h bar being equal to 3614.7 kilojoule. I'm sorry, you cannot see this. Kilojoule per kilomole. Okay, so in case I was writing here, but you guys couldn't really see me writing, sorry about that. All I did here in the bottom of the page, I had TR and PR, and I obtained that from the very beginning of the video. So I went to the table, figure A29, and I obtained ZH equal to 1.4. Sorry about that. I didn't really realize you guys are not seeing that. I'm gonna check the video, but hopefully that's just very short period of time. So anyway, our H bar is obtained, but this H bar is in kilojoule per kilomole. So what I want to do, I want to convert that into joule per kilogram, and you know how to do that. Okay, so my H is going to be H bar multiplied by 1 over M as before. So M is the same M that we use in part A. Now I have H bar, so that gives me H of a real gas being equal to 129 kilojoule per kilogram. So in part B, this is the H value that we obtained for nitrogen, 129 kilojoule per kilogram. In part A, we obtained 181 kilojoule per kilogram, but part A was coming from the ideal gas tables. Now, if you calculate the difference between these two, so just for the sake of practice, the difference between these two is going to be 181.4 minus 129 kilojoule per kilogram over this number, 129 kilojoule per kilogram, and multiplied by 100%. Let's see what is their difference in percentage. And that will be 40.6%. Okay, so this is the difference between the correct answer and the answer by assuming that the gas is behaving ideally. So obviously comparing A and B, the answer that we got here is closer to the real enthalpy, because in part A we assumed that the gas is behaving ideally, although we know that nitrogen is not behaving ideally in this problem. And the difference between them is 40%. So at the very end, what I would like to do, I would like to once again go back into this correlation, this scary looking correlation, and just discuss about what we have in this correlation. Or let me just go into this one. So what we have here, both of them are the same. I just changed the page. So what we have here, we have the difference in enthalpy on one side and also difference in enthalpy in the other side. But the only thing is on the left-hand side, this difference in enthalpy is for the real gas, and here the first term on the right hand side is for the ideal gas. Okay, so the difference in enthalpy in real gas is equal to the difference in the enthalpy of ideal gas minus these term, like the entire product of those properties. So the correlation looks scary, but in fact the concept behind that is very simple. If you want to find the enthalpy of a real gas, you want to use this. If you have two different states, you want to find the H1 and H2 based on that, and you can easily find the difference between them. Or if on the right hand side you have H1 bar for ideal gas and H bar 2 for ideal gas, then the difference of them, if you obtain the difference of them and subtract this, that gives you the difference of enthalpy of a real gas. So in this particular problem that we solved, we only had one state, but you can also use the same concept if you have two states.